Welcome. This is lecture 9.1, Neural Implicits and Point-Based Clothing Models. This is going to be part 3. In the previous video, we saw part 2, which was based on neural implicit models for humans. Now we will see how to make these models generative. So the previous models were also generative in some sense because they could generalize to new poses. But by generative here, I mean that given some control parameters, latent codes, for example, we can generate shapes of humans represented implicitly. So these works that we saw, like NASA, COPE, and NeuralGIF, SNARF, are not generative models in that sense. And so this is what we will cover now. So there's been a number of works in generative neural implicit models. I'm gonna base this talk on this work by Chen et al. To generate detailed shapes directly from a latent code Z. This approach is called GDNA, and the title is Towards Generative Detailed Neural Avatars. So the ideas are almost the same as what we've seen before. The only thing is that now we're going to train a model to produce those shapes from latent codes. So at a high level, the model will work like this. You start with some latent code that encodes the shape of the person. This encodes the overall size of the person and the type of clothing. And then you have like a latent code for the detail. This might encode things like, for example, like wrinkles in the clothing. And then basically this model, which is the canonical implicit model, produces in this canonical space like an implicit surface for the shape and a neural field for the normals. So basically a normal vector for every point in space. Let me adjust this for a second. All right. So this model is not subject specific. It could also generate these neural shapes for a wide variety of shapes. And so that's why there is this module, which is a multi-subject forward skinning, which is basically extending or adapting the skinning model of simple to these neural implicit fields. So basically, there's different modules, like one for the shape, which is M, and one for the skinning weights, which is W, and we'll describe them in more detail next. And this produces this post occupancy, or like this implicit surface representation, as well as the post normals. And this network is going to be trained using a 3D reconstruction loss, using an auto-decoding framework. And then in order to obtain the details, like these normals will be rendered producing a 2D normal map, and then like a 2D adversarial loss will be applied here also in order to learn this more stochastic component. So what does it mean, like auto-decoding framework for training? It means that you initialize a set of latent codes, Z detail and Z shape, for every instance in your training data set, and you optimize those along with the model parameters. The model parameters are parameterizing the canonical implicit model, the multi-subject forward skinning model as well. And for this part, the 2D adversarial loss, this is not trained using an auto-decoding framework. It's trained using like a GAN training. So this minimax game, which I think you will see in other lectures. All right, so let's look at the first component, which is the canonical implicit model. There's almost no new concepts here, but you can see here how those concepts that we've seen can be applied to build this system. So basically, like you have like the latent code Z shape, which will produce like these features. If you remember, like this IFNet features, which were like this voxel grid of features, this is the same. It produces like a voxel grid of neural features. Then for a given point, you basically do trilinear interpolation of these neural features that will be fed into this occupancy block that, together with the position, the absolute position of the point, will decode into the occupancy in this unposed canonic space. In addition, like based on the features and based on the absolute positions of the points in this canonic space, then the normals are also predicted. This normal module is also a function of this latent code, which is responsible for modeling the detail, right? So altogether, we have that the shape is represented as an implicit surface, because it's basically all the points X that satisfy that the occupancy is at the threshold, tau, which would be 0.5, and the occupancy field here is basically mapping between 0, 1, 0 being inside typically, and 1 being outside. And right, we have this mapping, which is this occupancy map, which takes the input point and the latent code Z and produces the occupancy as well as a feature. And basically this latent code is of dimension L shape, which is controlling the overall rough shape of the human, and Z detail would be another code that models these details that are baked into the normals, right? So we have these two mappings here, one for the coarse shape O and one for the detailed shape with normals, right? But this is right, this is modeling things in the canonic space, and now we have to model the pose dependency, and we also need to be able to train these and to model multiple subjects. So we need another module, and this module is very much based on SNARF, which we just saw before. It's based on this idea of forward skinning. However, here we have to be a bit more careful because this model is multi-subject, it's not subject-specific. So we need to model two things. One is the body deformations, like the overall body deformations without clothing, and the deformations with clothing. And to learn this forward skinning, we're going to consider the simple template without these like body deformations. And this will allow the network to learn easier. Okay, so let me explain this in more detail. So here we have this skinning module W that takes this latent code Z shape as input, and it also takes X star. So X star would be this size independent position of the point, which is basically canonicalized both in pose and shape as well. And then the skinning weights are predicted, and basically they are posed using LBS. How this actually works is using this trick from SNARF, which was basically you start from X prime and you need to figure out what the canonic point X star is in canonic space. And for this, you need to do this iterative root finding and differentiating through this process. So the process will be like, okay, I start with X prime and I have to satisfy this equation here, which is basically saying that X star I should find the canonic point X star such that that the post X star, given the shape and the pose and the latent code of the shape, matches the post point, right? So we have this implicit equation that we need to satisfy. So just a note on the notation, because it's easy to get a bit confused here. So here, notice that there's X star and also this like little triangle on the top, little hat. This means that it's the canonic point, but this point is in size-dependent space. This would mean a canonical space, including the shape of the person and the clothing, which we need to now make size independent with this module M in order to predict the skinning weights. That's why this X star and hat here has to go through M in order to like canonicalize it in shape as well, and then predict the skinning weights, right? So the new concept perhaps here is that this there's this additional module which canonicalizes the shape of the person such that we can predict skinning weights on this shape-independent space, right? And this is important to make the model generalize easier. All right, and the module M, which I just described, is basically this body shape-dependent warping field. And right, as I said, like the process is based on forward skinning. Right. So this forward skinning, again, is satisfying that the post point by our model, which is denoted here as D, matches the ground truth post point X prime, or the point that we're querying. Okay. And we have these two like canonic points, if you want, like the size independent X star and the size dependent X star bar on the top. And so that's the model basically, and it has to be trained using this auto decoding setup. So basically, you will for every scan that you have in your data set, it requires a data set of scans. Like you will initialize these Z shapes, like these codes, one of these codes vectors for every instance, and then you will optimize these codes along with these module parameters here. And then once you have trained this core shape model, then you can start training the normal module afterwards. This is important, and it's quite common in many algorithms that you first have to learn the coarse model and then you have to add the details on top later. Right, so these are some of the results that can be obtained with such a model. And as you can see, it looks quite detailed. It's generated from scratch. The deformation doesn't look particularly like dynamic, I would say. It looks similar to what you would obtain with a skinning model, and that's because, like, I mean, actually, it is a skinning model. Like, it predicts the weights, and there's no pose-dependent deformations here, as far as I can tell in this diagram here. The skinning weights, for example, do not depend on the pose. What could make it pose-dependent is this normals predicted. So we see a little bit of pose-dependent deformation, but not much. All right. But what is cool is that, yeah, these results are actually generated from latent code. So this is nice because you can generate then like arbitrary humans from this latent code. Here, like one can show like the variation in clothing styles and so on. So one problem that this model has, or one feature or limitation, is that it's basically a single layer. It does not separate what is clothing from what is the body. And we've seen in other lectures, like in the vertex-based models, that separating the clothing from the body has some advantages, like it gives you more control, for example. And so there's also like implicit surface models that are able to separate the body from what is clothing. So this is, for example, Simplicit, which is topology-aware generative model for cloth people. And here, encoding the clothing surface as a neural surface, as a neural implicit surface, then one can interpolate across different garments, including different topologies, as you can see here in this picture. So just to recap, vertex-based clothing models were based on displacement fields, which require predicting three-dimensional displacements as a function of pose and shape, right? So this was the case of TaylorNet. So if we had this function here, M, that based on the pose and the shape. Okay, this notation is a bit not exactly what we want to do. Like, actually, based on the pose and the shape, you would be predicting here a displacement at the output, right? And then these models, they need to specify the number of vertices or the number of displacements that you will predict. So they are not continuous. Now, in a neural implicit model, what you would have like is a function C that takes a point arbitrarily in space and a pose and some codes again to model the clothing, and it would produce an unsigned distance to model the surface, right? And so the surface would be at the 0 level set of this signed distance. Now here zcut encodes like how the clothing overlaps with the body, so things like sleeve lengths or pants, the trousers lengths, and so on. And the clothing style controls the size and fit, like how tight it is to the body. So this was a design choice to have a little bit more control on the generated results. Right, so the representation is based on an unsigned distance field, similar to neural distance fields that we saw before. And basically, given an input point, you will have an MLP that predicts this, this distance field. And this MLP, of course, needs to be conditioned on these clothing parameters, which is basically like this Z codes that I just described before. And once you train the model, like you have basically like this different attributes that can be like that can control the output clothing, right? So basically, like by moving along the principal directions in the latent space that the model has learned, you can interpolate different like clothing styles and cuts and shapes, basically. And this is what is being illustrated in this picture. So notice that, like in contrast to methods like TaylorNet that are based on templates, this allows you to, interpolate across different types of cuts and templates, which would not be possible using a mesh-based representation. You need this neural surface representation in order to model these quite varied surface topologies. Right, so here, like, actually, I should have described this a bit better. Like, these attributes were controlling different things. Like, one was the cut, the other one was this, like, sleeve length, and now that is controlling more like the shape. All right, just as comparison, like the TaylorNet like was producing results that were compelling, but notice that the interpolation was always within the same garment. It could not interpolate across different, completely different garments as Implicit can do. Right, so overall, like this implicit model can represent multiple topologies in one network, and there is no need to predefine cloths and train independently per template, which is quite convenient. What is also convenient is like fitting these models to images, because we can directly optimize the latent codes of this model. So starting with an image, you can extract the cloth segmentation using a neural network. Nowadays, there's a lot of good methods for doing this quite reliably. This method was relying on some initialization based on some work that estimates the body parameters and the pose parameters from the image. And then basically you can obtain a 3D reconstruction by optimizing the latent codes of the model such that it overlaps well with the semantic segmentation mask. And I'm going to explain now in more detail how this is done, because I think it's interesting, and the fitting objective, the optimization, is quite different compared to when you use like a vertex-based model. So this is the objective function. So you want to minimize this loss. You want to make this loss small. And the optimization variables are the clothing parameters. You could also have like shape and pose parameters here. But just to make it simple, let's assume that we know already what the shape and the pose should be, and we only optimize the clothing parameter Z. So now we have two scenarios. One, well, we first have to sample points around the canonical space. We need to pose them, and then we need to compare them against the image. And these points, P beta, are basically body relative representation of a sample point in canonic space. What does this mean? It means I sample a point, and I'm going to encode this point relative to a set of vertices on the mesh. So I'm going to predefine like the set of vertices, like let's say you take 100 key points, And then every point will be expressed relative to these key points. And so relative, it means that we just store a matrix of displacements from the key point to the point. And the reason is that this encodes how the point relates to the body. Otherwise, then you would not have this relationship, and then this would be harder to learn. So we have two scenarios for sampled points after posing them. One is that SP equals 0. SP is a variable that indicates whether the point overlaps with its corresponding segmentation label. Here, the t-shirt or the pants or the hair depends on where the point, depending on what the point represents. And then basically we have two scenarios. One, like the point does not overlap with this segmentation label, in which case this variable SP takes value 0. And the other case is when the point does overlap with the semantic segmentation label, in which case this variable takes value 1. Now, in case the point lies outside the surface, what do we need to enforce? We need to enforce that this point belongs to the outside of the surface. So we need to enforce that C here produces a distance that is bigger than 0. And in particular, it needs to produce here what is predefined as D max, which is like the maximum distance allowed by this model. So we cap the distances so to make the model more, easier to train. So this is forcing the point to be outside the surface if it's basically not overlapping. And if the point is overlapping with the semantic segmentation mask, we need to make this point belong to the surface. How do we make the point belong to surface? Well, we have to ask that C, which is this distance field, equals to 0. So this is what we're doing here. We're minimizing this absolute norm of C, which basically would mean that we have to make this C equal to 0. This I here, all right, this is taking the minimum over the points along the ray, because there might be multiple points that project to the same pixel. Basically, you consider the minimum along points sampled along the ray. So actually, points are not sampled randomly. They are sampled along the rays that go from the camera center through the pixels. And basically, after doing this, you will sample lots of points, and then you can recover like these surfaces that are, aligned with the semantic segmentations in the images, and they are on top of the body. And yeah, combining this flexibility of implicit representations with the explicit control of parametric models like Simple, we can recover these layered models from images. Now, the quality here is not great, but that's not a deficiency of the model. It's rather a deficiency of the data that was used. This data was based on simulations, and the quality of the data was not great. Another problem was that we are using here a threshold on the distance field, and that creates like a bit thicker clothing. Maybe a trick like what we did for neural distance fields would have produced a little bit more detailed results. All right, so overall, just to remind you, this is more or less my take on this. And I mentioned before that implicit surfaces are more compatible with learning, but they are not allowing so much control. But you can see that these models already allow some degree of control, and so this is basically improving over time. All right, there's a lot of papers, and this is only going until 2022. I think more recently there's probably even more papers coming. So yeah, you're encouraged to, if you're interested in this topic, like to check these other papers as well. All right. Now let's move to part 4, which is point-based clothing models. This is going to be a bit briefer than the other parts, but it's a representation that it's worth knowing and being aware of. So this is the table that I was showing before, and so we see here, like in terms of control, topology, details, speed, and whether the representation is continuous. Now the question is like, how do point clouds compare to other models, right? So let's look at this. So there's a number of papers that actually are based on points, and in general, they are high fidelity and they have flexible topologies because the points can move to different locations, and they are basically also learnable directly from scans, and they allow for fast rendering. And actually nowadays, like with the rise of Gaussian splatting, which is like essentially a point-based representation as well, I think this representation is becoming more and more popular in the community. All right. Yeah, so previous methods that basically are exploiting some sort of point-based or patch-based representation, they were like attaching features to patches of the surface. However, like this is the work of Ma et al. 2021, which basically results in patchy artifacts, because when you put things together, so basically you have like artifacts at the boundaries. And like this work, which is called POP, is basically attaching features directly to the points. And so this allows to get a more fine-grained representation, which results in sharp local details. All right, so how does this work? So this work in particular relies on a UV map. Remember, the UV map is like this image that encodes at every UV location, like yeah, there's a correspondence for every UV location on the image. There's a corresponding 3D point on the surface. And so basically what this is, how this works is you have like a pose encoder that will produce like these features for every UV location. And then basically there's a garment tensor variable that encodes the clothing. And basically then based on these point-based features and the garment features, like there's the shape decoder that predicts a displacement, essentially Ri, for every point in the surface. So every point here that stems from the UV map is displaced along Ri in order to model things like skirts or complicated clothing. So the mapping that you learn is a displacement field, and this is defined on the surface. So you have like a mapping from UI, which is a UV coordinate, and RZ, which is the latent codes. And this maps to this displacement vector R that belongs to R3, which is Ri. And then a point in the post space means that you need to transform this displacement, which is predicted in canonic space. And the original point needs to be also transformed to PI, which is in the post space. So this model might look very reminiscent of TaylorNet, because essentially TaylorNet is almost the same. The only thing is that TaylorNet specifies the, let me think, what's the difference? This also specifies the number of points. Okay, now I don't know if this model spits out a fixed number of points or the model is continuous over U coordinates. Could be. But one difference is that in TaylorNet, you assume a given like connectivity of points. Here, the points are disconnected, and just the network just spits them out, and then they are rendered without making use of faces that connect them. Right. So these are some of the results that can be obtained. And like in general, like in the paper, it's demonstrated that this produces higher quality results than LBS. Due to these simple UV maps that are used, there's some discontinuity, which can be seen in this like seams. Like this is where the UV map cuts the surface into two. And yeah, so this is more significant for skirts. You might have this type of artifact. So for example, like one problem is that if you have 2 points and they are attached to, for example, like the left leg and the right leg, when you're doing skinning, when the legs get separated and these points get separated, and therefore like the points here get a bit sparser, and then the results look also not so great. See, this is a problem of displacement fields. Like if you have a displacement field from the body, you will have this sort of artifacts, right? Okay, so so in comparison, I would say that points are also not so complicated to control, and you can model different topologies. They can achieve like a good level of detail, and they are fast, but they are not a continuous representation. They are discrete still. So in that sense, they are suffering from the same problems as meshes, that you need to pre-specify the number of points that you will produce. Yeah, we will see later in the lecture, this we will discuss like point-based models, which are based on Gaussian splats, and the main difference is that now, like in every point, you will attach a Gaussian with a given covariance, which can be very quickly rendered, and which can produce like high quality results without having this like connected, set of vertices. All right. This concludes the talk. Thanks to Julian, Enrique, and Chanli, who have contributed to these slides. And also, if you're interested in this topic, you can check this lecture. Maybe this lecture is now a little bit dated, but it was like neural implicit representations for 3D vision, which basically describes like the pros and cons of these representations. Thank you, and I'll see you in the next lecture. Let's stop here.